Those two displacements are being added independently
Oy.
along the
There's
x-axis
two
and
of
the
me. Wait,
y-axis.
sorry.
So
Oh my
the
God.
Toyota,
Hold on.
right? The
Hold
Toyota,
on. Sorry.
Yeah, here's
Good afternoon, Professor. I think you are on mute.
Yes, sorry. Thank you. Thank you. Okay. Good afternoon, Latitude. Thank you for that. Sorry. Oh my God. There's a reason that was on mute. Okay, hold on. Hello. Excuse me. So good afternoon, Jamie. Good afternoon, Montserrat. Good afternoon, Madonna. Good afternoon, Latitude. Thank you. Good. Okay, more people coming. Good. Hello, Ali Rat. Okay, awesome. Sorry. Yes, I was on mute because when it first, good afternoon, Amelie. Excellent. Okay, here we go. Oh, that was embarrassing. Okay, good afternoon, Josh. Okay. Okay, I think we are here. Yes, good afternoon, everybody who is here. Okay. Bear with me for and good yes, okay, so that's everybody. Hello. Okay. We will get okay. So we have two agenda items for today. Pardon me for a second. We have two main agenda items for today. One is I want to walk through the end of that homework that was due today, the homework that we started in class last time. Excuse me. What we did last time was meant to introduce the concept of fields, to derive that concept from the concept of electrostatic forces. So the second part of the homework, the sort of perhaps more computationally involved part of the homework, asked us to compute the field at a certain location in space due to 2 point sources somewhere else in space. So one main agenda item today is I want to walk through that computation because it is important and it is not totally easy. The other thing, though, is I want to discuss I want to relate things directly to what you're doing in lab. I want to hear about what's going on in lab. I want to answer questions about lab. I want specifically to relate. So what we're doing in lecture is electrostatic fields. I want to relate the electrostatic fields that we're thinking about in lecture to the electric circuit that you're analyzing in lab. That is the other main goal. And I will say that second goal may even be ultimately more important, maybe, and certainly more engaging, perhaps. But that second goal is going to be done through discussion. So I am going to wait until. So I'm going to do the first thing first. I'm going to walk through the homework, like right now, while we're all sort of getting warmed up and awake or revived or activated. And then in the second half of the period, I really want to turn this into a bit more of a discussion. Good afternoon, Sebastian. Good to see you. Good to hear you. Good to read you. Okay, so again, the agenda is I'm going to walk through this somewhat tricky homework. First half. Good afternoon, Yechan. Good to see you. Good to read you. I'm going to walk through the homework first. Then we're going to discuss as a group. We're not going into breakout rooms. We're going to stay as a group, but we're going to discuss what's going on in lab. You're going to fill me in a little bit from your perspective. Obviously, I have Professor Moses's perspective. but I'm going to get your perspective. I'm going to answer questions you might have, or hopefully, and discuss our way into a connection between the homework stuff, the homework material, and the lab material. Okay, so that's the agenda. I'm going to switch my board here. So that you know, to be clear, I'm going to switch the screen share for a second here. What I'm about to go over is this. If you want to take a screenshot or anything, this was the business, that we did last week, right? Like in class, we started this homework in class, in breakout rooms, et cetera, et cetera. You guys did this part in class. The ultimate purpose of this part, it was sort of repetitive computations that were meant to ultimately show that if we wanted to cut down on the tedium of electrostatic force calculations, we can sort of package a bunch of the information in advance and call that package of information the electrostatic field, right? And so in some ways, so I'm just reviewing that for a second, in some ways, the purpose of these repetitive calculations was to get us to see that electrostatic field is in a way an advanced computation on, it's an advanced computation on electrostatic force. As we decided last week, the electrostatic field is the amount of force that a known source charge would or will exert at a known distance from. Oh, that's interesting. Okay. That a known source would or will exert at a known distance from a test charge. And the test charge is always defined to be +1 coulomb of charge. So what a field is what will happen. Put one last final way again. I always say, put another way. A force is something that I do to you, but a field is something that I do to a point in space, right? The field is the prediction of what will happen to any second charge that could or would or might land at that point in space. The field is all the information, all the possible information of the source, of the force waiting to happen, all the information that constitutes the force that will occur, except for the vital piece of information of what second charge is going to receive that force. Because the bigger the second charge is, the bigger the force will be. So the whole idea of the field is, and maybe you should write this down quickly if you're still with me, like field is force per charge, right? Like capital E equals capital F over lowercase q, and that's a triple equal sign. Field is defined to be force per charge. Therefore, and the whole purpose of it is that you can flip that equation around and say force equals charge times field. And that's really the meaning of it. The force that some small receiving innocent charge will receive or experience, the force that some charge ever, like some little electron or some proton or some clump of protons condensed into like a Euclidean point, some amount of charge that's like traveling around through space, the force that it will receive and experience will be how big it is, the size of it, lowercase q, times whatever field it finds itself to be in at that point in space. The field is the package of information waiting to apply a force to any receiving charge that might come along. The field is sitting there whether the receiving charge comes along or not. So the field is the force waiting to happen. Again, field is force per charge. Force is therefore field times charge. That's the idea. And that's that's the summary of what we were like slogging through last week. In the beginning of our construction of this, the field is just a mathematical trick in our minds to save us computational hassle. It's just all the numbers bundled together, just waiting for the final number. It's our way of saying we don't need to rethink this through every single time a different test charge, a different receiving charge comes along to a particular point in space. Like, as long as we know everything that's happening at that point in space, we could save a lot of steps in this calculation. That's how we first sort of think it through. But then we eventually realize or come to believe that that's not just in our heads. That information is sitting there at the point in space, waiting for the charge to come along. And it's sitting there the way we represent it in our heads. This information, the field information has magnitude, i.e. has size, and it has direction, because the field information is force waiting to happen. And force has magnitude and direction. You get forced by a certain number of newtons in a certain way. So the way we picture field is, the way we picture the field due to some source is, we picture a bunch of vectors everywhere in space. We picture that at every given point in space, due to a certain source, at every single point in space, due to a certain source, there is a vector sitting there. Its length indicates how many newtons of force will be exerted on every 1 coulomb of charge that ever comes along to that point in space. And its orientation, its tip to tail orientation, indicates in what direction will that positive 1 coulomb of charge be pushed or pulled, right? So, okay, so we now have this picture that that every time you put a source into the world, into space, into the universe, into the lab, every time we put a source somewhere in space, it creates a field, a bunch of vectors everywhere else in space. I keep saying a source. What do I mean by a source? I mean a charge. I mean a proton or an electron, or more likely a bunch of protons or a bunch of electrons, like squeezed together in some shape at some point in space. Protons and electrons are the source of electric field, electrostatic field, and protons and electrons, on the other hand, are the receivers of electrostatic field. This is the picture. Bottom line is, anything you ever think you understood about electrostatic force between and among protons and electrons and other protons, whatever you ever understood about the pulling and pushing between protons and electrons, we're now saying, yes, take that understanding, but break it apart from the object. Instead of believing that a proton over here pulls on an electron over there, we're now saying proton over here creates a field everywhere. And if an electron lands anywhere in that field, it gets pulled or pushed, well, in this case, pulled by the field, by the vector that it is sitting on in the field. That's what we're saying. That's a summary of what sort of oh, and good. I'm glad we've got some video going and it's some avatars. Okay, I feel like, okay, so that's what we're, so thank you. Yeah, I appreciate it. You don't know what it's like being me. Yes, you do. And also, I don't know what it's like being you. And yes, I do. And I know it's a lot tougher than being me. I totally get it. Right. So that's a summary of what we did last week. Now, and that's the summary of like the first half of the homework. Then the homework was due today. And again, as always, I know some, I'm going to now walk through the second part of the homework, which is this. That's what I'm going to do now for people who, okay. And for those of you who've already done it and already handed it in and already gotten a huge number of points just for handing it in on time, huge, I might add, for handing it in so thoroughly and promptly, you follow along and hopefully you'll have questions about what those of you who've done it, hopefully you'll be knowing what you're looking for as I'm talking. You'll be finding out whether you did it right or wrong. Quark willing, you did it right. And then everybody's happy. And then I owe you like 4 more points or something like that. And you'll let me know. But if you made any mistakes in this and then you find out you made mistakes as I'm going through, then of course you can correct them. Of course you can re-upload and get all the rest of the points. I'm all for that. Again, hopefully those of you who've done it will have sort of an easier time paying attention to what I'm about to do because it is a little bit thick and at least you'll know where I'm going with it. For the rest of you who didn't do it yet, can you benefit from this discussion and and figure it out how to do it later for points? Yes. I mean, okay, I think it's easier to pay attention if you've already tried it, but I think it should benefit everybody and everybody can still get the points for it. And yes, a problem like this is usually on the final exam. So what I'm trying to say to everybody who's here is for the first half of today's period or the first section, I'm going to try to solve, I'm going to walk through the solution to this thing that was assigned for right now. It's not easy. Okay. It's a little bit thick. It is what it is. It's a thick computation. The computations from last week were repetitive. Maybe they were tedious, but they were tedious. They were kind of repetitive, but I could, from all the breakout rooms and everything, it felt like people knew what was going on. I think that at least by the end was clear. To warn you, this thing that we're about to do today, it's not repetitive in the same way. It's actually kind of thick. It almost feels like science or something like that. So I will ask you to bear, it does require some attention. I will ask you to bear with me. I will encourage questions about it to stop me, whether you've tried it yet or not. And we're not going to do it for the whole period. We're going to do it like starting now for a while. Then again, for anybody whose attention I now have, then again, when we're done with this, then I want to turn this into a more of a discussion with all of you about what's going on in lab. I want to start, I don't want to help you with what's going on in lab, i.e. circuits. This right now, last way I'm going to say this right now is about the more abstract notion of fields. Fields are abstract, but they're very, very real. Please remember, they are sort of the second beat in this course, the second example of an unthingy thing in nature. First, we had waves. Now we have fields. They are both deliberately abstract notions. A wave is not a material object. A field is not a material object. Yet we believe strongly that they both exist and affect the material world profoundly. So they are like the heart and soul of this course, things like waves and fields. In lab, you see the concrete manifestations of electric fields. You see circuits. That's where they come alive and do stuff. It's not easy to see, obviously, the connection between an abstract electric field and a practical concrete working circuit. That connection is what I want to get more into the second half of this period. But all right, enough talking. I'm going to start solving this problem. Again, if you don't have the sheet, if you haven't done it, I hope you do take notes and you can figure out how to do it from this. But if you don't have the sheet at all, please take a screenshot right now. This is what I'm talking about, right? Because I'm going to switch boards in a moment. So, okay. But this is what we're doing. This business here. Hold on. Okay, so this is the I believe. This is the situation. All right, I'm just. Oh, and hello. Oh, and hello. Okay, the screen's great to see Madonna and Tiggy, as well as Josh. Great to see you. And I'm not saying it's not great to see all the rest of you, but and I'm also not saying it's great to not see the rest of you, but it's great to have the rest of you. Okay. So this is a situation. We've got a coordinate system. We've got 2 point charges in the coordinate plane in the 2-dimensional space in which we're working. So those 2 point charges are what I'm considering the source of electrostatic field. Each of them is creating its own contributions to the electrostatic field everywhere in the world. In fact, let me be clear. If I think it does ask, let me be like, if we zoom, like if this is Q1, I'm just zooming in on it right now. It itself is creating field contributions everywhere in the world that look something like this. What I mean by this is that due to if Q1 were the only thing in the world, and Q1 is a positive point charge, right? So you can picture it. You could picture it as like a little proton sitting there at that point. More realistically, since it says it's a point charge of magnitude 5 coulombs of charge, right? So 5 coulombs of charge is actually a lot of charge. Like 1 proton, I think we said this last week, has a charge of only 1.60 times 10 to the negative 19th coulombs. Like, not that you're supposed to memorize that number, but just recognize or have a feel for the fact that that's a tiny, tiny number of coulombs. So if this thing is 5 coulombs, realistically, what we're saying is this is about 80 quintillion protons jammed together into like a tiny, tiny point. It's like how many angels can dance on the head of a pin. This is like how many protons can you fit in a tiny point? And the truth is you can fit a lot, right? Like maybe this number is slightly large to be realistic. Like it's a little bit hard. It's a little bit hard to have like a 5 coulomb positive point charge, but it's not that hard. And 5 isn't that beyond the scope of possibility. I mean, it's a rounded up number to make the calculation easy. So what you're picturing, first of all, just so you can picture what the heck we're talking about in this problem, like there's a clump of protons all jammed together into a point, like, into a 0-dimensional dot region of space up somewhere in space. And what we believe, therefore, I'm just zooming in, down and to the left. I'm just trying to zoom in and give you perspective on it. We believe that, therefore, everywhere in space, there's an arrow shoving out from this Q1. All the arrows are arranged radially. They're all coming out in radial directions in 3 dimensions of space, and they're getting shorter and shorter by the same, get farther and farther away. Like that picture is saying, if there was nothing else in the world or nothing else in the lab, if a little other positive test ever came along and landed on anywhere in space, it would land on one of these arrows. I'm just drawing representative slice of these arrows. It would land on an arrow, and the arrow that it lands on would tell us how hard and in what direction it would be shoved away due to Q1, right? That's what this picture is trying to represent, that automatically by Q1 being in the world, there are arrows everywhere in the world trying to shove away any possible test charge, any possible 1 coulomb of charge that would land anywhere in space. Like that's the idea, right? That's due to Q1. Due to Q1 where people come in. But at the same time, so all those arrows are technically called field contributions because Q1 ain't the only game in town. It's not the only charge in the world. There's also this Q2 right over here. Now Q2, again, I'm just zooming in, just try to give some perspective on this. Q2 itself is creating field vectors everywhere in the world. And they're also getting smaller and smaller as they get farther and farther away radially from Q2. But notice, it may not surprise you, these arrows are pointing in. Why? Because the whole idea of the field is it is a prediction, or it's a package of information that says what will happen to any positive 1 Coulomb of test charge that ever might land in the world anywhere in space due to that source. So the point is, and this is a little bit of a tricky subtlety. It certainly used to throw me in college, honestly. Like whatever we ever say about fields, we're always assuming we're talking about the force that will be exerted on a positive 1 Coulomb test charge. Again, we always call it test. We always call the receiver a test because, as like we were finding out last week, the test is a test. It's hypothetical. It doesn't need to be there for the field to be there. The field is what will or would happen if the test ever arrived. And the field is what would happen to a positive 1 Coulomb test. So if a positive 1 Coulomb test ever landed in space anywhere in the region of Q2, it would be attracted to Q2 because Q2 is actually negative, right? I mean, just because we're told in the problem, Q2 is a negative source. So negative sources always pull in, positive sources always push out, because the whole thing is a prediction of what would happen to a positive. And summary, sources can be whatever sign they are. Sources can be positive or negative. The test is always assumed to be positive. Last bit on this, because people often ask, like, am I saying that when I say that the test is always assumed to be positive, which I am saying, am I therefore saying that like a negative can't ever come along and experience a field? Am I saying negatives can't land in fields or experience them? No, I'm not saying that. A negative could come along and experience a field. It's just that whatever it'll experience will be the opposite of what the field says, like literally. Like in other words, if each one of these arrows is an indication of at that moment how hard and in what direction a positive would be pushed, then if a negative did come along, it would go the opposite direction of that arrow, like literally. Just like, okay, last thing I'm going to say on this. The field, in the same way, a field is a prediction of what would happen to 1 positive Coulomb of receiving charge. Does that mean that a point charge of magnitude 2 cannot come along? No, it totally can. If a lowercase q of 2 comes along, then you multiply the number 2 by the field, and you'll get a force twice as great than what you would get for a receiving charge of 1. That's what we mean when we say F equals Q times E. Okay, so anyway, and of course I will stop if there are any questions. Okay, so down below is a blow up of what each one of those charges is doing to the universe. Okay, each one of them is making a whole bunch of field contributions to space. Our goal is to find out what the net result, what the sum of those contributions is at some given point in space. Like everywhere in space now, there's arrows from one, and everywhere in space, there's arrows from the other. At any point in space you pick, I hope this is clear, and please stop me if it's not. At any point in space you pick, you'll find there's a vector arrow pointing from one dude, and there's a different vector arrow pointing from the other gal. Like any point in space you pick, due to this situation, like we're isolating our attention on a situation where there's 2 point sources somewhere in the space of a lab or the space of outer space or something. But anywhere you go, you would find 2 vector arrows sitting there at space. And the net effect of what you would feel, the field that exists at that point in space, would be the vector sum of those 2 arrows anywhere in space. So we could, this problem is asking us to pick an arbitrary point in space and compute the sum of the 2 vector field contributions. We are going to now do that at the origin of this coordinate system. I'm trying to emphasize right now that the origin of this coordinate system is just an arbitrary spot. We're going to compute the goal. The goal is compute the E vector, the total magnitude and direction of what the E arrow is doing here but we're just doing it there just because that's a point that we're picking. The problem could be asked at any point in space, and the whole procedure would be the same. Okay, so that's what we're trying to do. I'm just looking at the chat. Okay, I don't know if it's a good sign or a bad sign that no one's asked anything yet. This is probably a good sign. Okay, so we're good. So that's the goal. We want to compute the E, and we're going to say that the total E, the sum of the E field there, is going to be equal to the sum of the E field contribution from charge one plus the E field contribution from the other. So we're going to do the vector sum of these two field contributions. Now I'm saying vectors. I'm going to just draw a quick sketch. I mean, as the problem asks, of the vectors that we're adding together. Okay, I'm looking at Q1 right here. Q1 is positive. It's up. Oh, and sorry, I'm going to add one more thing. Everything to the right, I'm calling positive, of course, but I'm also, just for English perspective purposes, I'm going to say that everything going to the right is east, and everything going to the left, which is negative, I'm going to call west, just so that in my final answer, I can express it in terms of points on the compass. And I'm going to say everything going up or positive is north, and I'm going to say that everything going down is south. That's not really important. I'll just make it clearer at the end. Okay, so I'm saying there's this positive point source called Q1, which is up to in the northeast of the origin. It is positive, so it is pushing out everywhere. In particular, it's pushing out on the origin, as per this diagram in the lower left corner of the page. So it's going to make a vector contribution. Excuse me. It's going to make a field vector contribution that looks something like that, right? That's the field vector contribution from Q1. I'm calling it E1. It's down, right? It's a push. So if you were sitting there at the origin and all that was going on was Q1, you would feel that. You would be pushed that way with that approximate magnitude. I'm just sketching it. I'm not doing the magnitude exactly because I don't know the magnitude exactly yet, because that's what I'm about to figure out. But that's roughly what's going on. But now from Q2 is also affecting that point at the origin. But Q2 is negative. So Q2 is pulling on the origin. Right. So there's going to be an arrow coming out from the origin going the other direction, pointing to Q2. I think it's going to it's going to look something like this. I hope you understand what I'm doing. I'm like, if there were a dotted line, I'm trying to draw on the line that connects from 0 to Q2. It's obviously less steep than the other one. But notice something else about it. So notice something else about that field vector. Number one, it's pointing the other direction, but number two, I'm deliberately drawing it as shorter. If I were doing everything perfectly to scale, already had done all the numbers, I would know exactly how much shorter to make it. I don't know exactly how much shorter to make it, but I know to make it shorter. I'm going to take a risk here. Should I take a risk? Should I take a risk? I'm going to take a risk. I'm going to ask if anybody has any desire in the direct or public chat to speculate, or yes, this is the part. Okay, so I'm going to ask for a brief moment. I'm so afraid to do this in the chat, or with your voice, or with like semaphore flags, or with a small interpretive dance. Would anybody maybe want to suggest why am I roughly predicting or conjecturing that the field vector from E2 is substantially shorter, i.e. weaker, than the field vector from E1? Like based, like I'll repeat the question again in 1 second, unless, oh my God, they look like, I think just based on what was told to us in the problem, like I haven't done any calculations yet. I'm going to have to do calculations with these two arrows, but I believe the arrow from E2 should be shorter than the arrow from E1. Does anybody want to privately speculate or publicly speculate as to why? I am guessing, and it's not really a guess. Like, honestly, I mean, I'm being silly. Like, I know that E2, and you do too if you think it through. It is actually necessarily the case from the numbers given in the problem that E2 must be a weaker field contribution then E1. Oh, wait, I see something in the direct. Oh my God. Dude. Okay. Or dude, all right. I'm going to say this. I see one thing in the direct chat. First of all, that excites me. First of all, I could retire right now. Thank you. But then I'd be the one that would have to find you a new teacher, and Jacob is totally overworked. So no, I see something in the chat. One thing, so that person who did it knows who I'm talking to, him or her. Second of all, the thing I see in the chat is totally correct. I'm going to say that too. I'm excited. Third of all, it's so correct and it's so clear that it's making me realize that there's actually there's more than one correct thing that could be said about this. So at the risk of pushing my luck, I'm going to say, first of all, congratulations and thank you to the person who's in the direct chat. But second of all, I'm even going to wait a little bit longer for at least one more thing, because there's the person like laid out the argument so clearly that it's clear to me that there's more than one argument that could be laid out. So I'm going to wait because I'm a jerk. But yes, thank you for and I won't wait forever, but I might, because I'm tired. So I'm going to repeat the question though. Also, I will accept anybody who puts in the chat. I totally hear the question. That anybody who just even writes the question. Oh, make a portal for that. If anybody even wants to just write in the chat what the question is that I'm asking, to show that you're alive and you're with me, but you still but you're at bay with an answer, I would be perfectly heartwarmed by that. So I will repeat the question and see if this works. You see how desperate it could be on it? Okay. The question is, how do I know that the E2 arrow needs to be shorter than the E1 arrow? Because I do know that. Oh, there's another thing in the direct chat. Dude, or dudette and dudette. Yes. All right. I now have two things in the chat that are both, first of all, giving meaning to my life, and which it's not all about, but it kind of is all about. But second of all, they're both correct. And I'm psyched. Okay. I'm not going to torture anybody anymore. I'm very appreciative of the two people who wrote in the chat. I'm appreciative of you all. We're all going to heaven just on different trains. Some of them are local, some of them are express. Both people in the actually though, I'm afraid that I'm only talking to the people that already know the answer. I am going to wait for one person to put in the chat what the question is, even if they don't know the answer, so I can make sure I'm actually. So I'm even going to say it again. The question is, how do I know that the E2 field contribution is weaker than the E1 field contribution? The minute someone just even repeats that question in the chat, then my life will really be fulfilled, and I'll stop saying that, even though I totally won't. Because I don't only want to explain this whole thing to the people that already know the answer. Oh, okay. Yes. Oh, wow. See, I really shouldn't be so obnoxious. You deserve better, all of you. Yes. Yes, exactly. Awesome. And there's things in the chat. Yes. I'm so excited by this that I'm not even going to worry that XT000G's iPhone might actually be like an enemy infiltration. No, I know it's not. Okay. Yes. Okay. So that is my question. Yes. Thank you guys. And thank you for playing along and joining me in group therapy. Yes. And the answer, one major answer that two people put in the direct chat is, look, the charge, and thank you. And I won't mention my name because it was direct chat. The charge, but they should submit for points, I might add. They really should. But everybody should. Q1 is a stronger charge, a bigger charge. It's 5 coulombs. And E2 is a weaker charge. It's only 2 coulombs. And even putting aside that one's positive or negative, because that just affects direction, the whole point is that a 5 field, actually all of this is all based. It's all coming from Coulomb's law in the first place, which is this. It's all about the bigger the charge, the bigger field you make, and the farther away something is, the weaker field it experiences. So first and foremost, yes, thank you. E1 is a big charge. It's making a big field contribution. Q2 is a small charge. It's making a small field contribution. That's what two people put. Thank you. And I know other people are thinking that too. I do. But second of all, can I also point out that what also matters is distance. And this could have been a confusing problem where one of them could have had a big charge, but a far distance, or vice versa. And then there'd be a conflict. And then we'd really have to look at the numbers. Which we are anyway. But also, I just want to reinforce, Q1 is also much closer. My diagram doesn't really indicate much, but Q1 is closer. It's at the coordinate 5, 4. Q2 is farther. It's at the coordinate 10, 3. So there's also the fact that when you're at the origin, you're farther away from Q2. So you're farther away from a weaker charge. Oh, yes, you're going to experience a weaker field contribution. Okay, so I'm just looking at that. Okay, so what we're now going to do, we're at the origin. And thank you again for indulging all my silliness. I think it helps. Not the silliness, the indulgence. So we're at the origin. We now have these two arrows that we're experiencing at the origin. Our job is to add them together. This whole problem is just going to be an addition problem. We're just going to add two arrows together. But the arrows are a little bit abstract and a little bit mathematically complicated, so it takes a little work. Our job. Okay, now the first thing we have to do, this diagram here is a picture of the situation, but now our job is to add the two vectors together. This is a little bit subtle too, perhaps sometimes confusing people. When we add vectors together, we place them tip to tail, right? So just to visualize the situation, we have this picture, but to visualize the net effect of this situation, to visualize the vector sum, I'm going to make a new picture. I'm going to move the arrows, slide one of the arrows so that the tail of one is at the tail of the other. See what I'm, right? I mean, and I'm allowed to do that because vectors, in the whole thing of vectors, really the power of vectors is that you can move them around the page. It sounds so silly. And again, I'm not making a joke now. It took me at least 15 years really to realize this weirdness, but that vectors are computational tools and their power lies in our ability to slide them around the page and place them in different arrangements. It's their arrangement that actually does the math. Because right here, if I place them tip to tail, that means I'm doing addition, and it means that the vector that I could imagine or draw, or the completion of the triangle that I could interpolate, that goes from the original tail to the final tip, that vector that completes the triangle is the answer, right? This thing, and I'm going to blow it up. I'm going to zoom in on it. This thing right here, with some angle measured from the imaginary horizontal. I always measure my angles from the horizontal. This vector right here is the sum of the field contributions that we're looking for. In other words, two things. Number one, if this whole original diagram had been drawn to scale perfectly, right? If I had measured everything out with a ruler and a protractor, then honestly, by shifting the one brown arrow over to the other brown arrow and making that triangle, if I made it with a ruler and a protractor and everything, then that blue final arrow would be the answer. And I could just measure it with a ruler and a protractor, and I'd be done. In other words, vectors are that powerful that the picture actually does do the math for us if we're doing everything precisely. But I'm not. But this is now, this blue thing here is a sketch, a prediction, representation our final answer that we get with all the calculations should resemble this. Really, what I'm saying in the end is, if we get our final answer for what I'm saying is, if our diagram is roughly to scale, then we are believing that if you are sitting at the origin, the net effect of that proton over here and that electron over here, the net effect of it is that you're going to be shoved some amount to the southwest. I like the westernly components of those two arrows, are the westernly component of the arrows is dominating and the southerly component is dominating, and the net effect of those two charges that you'd be shoved down and to the left. If in the end, when we do all our work and get our answer, if it's different from this, then we have to stand back and check something. Like this is an advanced check on our work. Okay, enough of that. But that, okay, so that's our picture. So now we have to analytically do it. Okay, we're good. Oh, sorry. I'm looking at chat. Okay, so we're adding by components. Okay, so how do we do that? This is all still all Galileo extrapolated into all computations, like what we really believe. We believe that the laws of physics are the same in all coordinate systems, whatever coordinate system you pick, as long as it's unaccelerated, the laws of physics are the same. So the laws of, and the simplest, most limiting coordinate system I can imagine is a axis. Long way of saying, I believe the laws of physics govern over the x-axis of space. And I believe that independently, but simultaneously, the laws of physics govern over the y-axis of space. I can't, so any two-dimensional problem I ever face, I can and should regard it as two one-dimensional problems that are occurring simultaneously, yet independently. In fact, I'm going to write that because it's so important. Every two-dimensional problem or experiment Okay, so I'm saying that right, so this is really two one-dimensional problems that are occurring at the same time, but are not affecting each other at all. What does all that mean computationally? It means I'm going to zoom in on each of the vectors and divide them up, resolve them into their individual perpendicular components. I'm going to first zoom in on the E1 vector contribution. Zoom in on E1. E1 looks like E1 looks like that. Okay. So here's E1. And I always, well, here's E1. And I'm saying E1 is pointing to the southwest. Anything that points to the southwest is really, any field that is pushing to the southwest is really some field that's pushing to the west, while at the same time joining some field that is pushing to the south. Like this is the whole walking through New York City idea. If you want to walk northeast in New York, in Midtown Manhattan, you walk some amount east and then some amount north, and you'll end up at the correct place. Now, and you'll notice, I say when you want to walk northeast in Manhattan, you walk some amount east and then some amount north. You could say, I could have said it the other way around. I could have said you walk some amount north and then some amount east. And yes, that would work, but I never draw my vectors that way. I always, this is a pro tip right here. I always, whenever I'm drawing vector, I always draw my horizontal vector first, and then from the tip of the horizontal vector, I draw the tail of the vertical vector. That is a major pro tip when you're trying to resolve vectors. When you're doing anything with vectors, the minute you're putting together a right triangle or breaking something up into a right triangle, always, first of all, the legs are always tip to tail. The whole idea is that the two legs of a right triangle add together to make the hypotenuse. If there's any vectors on your final exam, please watch your tips and tails. And the strategy is always draw the horizontal first. And I'm saying it over and over again. I'm going to say it right now over and over again, because it's not like you couldn't do it the other way. Like, okay, here we go. Here's this arrow. I could, don't do this. Don't do this. If you're paying attention, don't. I'm just showing what I could go like this. And a lot of people will on exams. I could go down. I could go down and then I could go over, and there's nothing looks wrong about that. It looks totally valid. And in fact, technically it is valid, but it's going to end up messing me up in a big way if I do that, because in short, the angle between the tails, then the angle between that vertical faint arrow that I just drew faintly because I want to erase it in a second, the angle between that and the hypotenuse, the angle between the tails, the angle that is supposed to indicate the direction of the hypotenuse, that angle will be measured relative to a vertical. And that means it won't be an angle that's telling me how far of west. It won't be telling me southwest. It will be telling me west-south. It's an ass backwards angle. And it'll lead to English that is ass backwards. And pardon my language, I'm going to get attention. But what I'm saying, I don't know if that makes sense. Or what I'm saying is, in the end of the day, any angle we ever look at in these, let me back up. We're doing SOHCAHTOA and all that stuff. And a common issue with people doing SOHCAHTOA or doing trig, a common issue that some people are consciously annoyed by and some people are unconsciously annoyed by. A common issue is people understand SOHCAHTOA and understand, okay, the adjacent over hypotenuse is the cosine of the angle, blah. But where people get stuck doing it on their own often is they're like, yeah, but which angle? There's always two angles to choose from in a triangle. And unless the teacher tells me or the professor tells me, I don't even know which is the angle, right? Certainly that used to bother me. And it bothered me way before I even knew that's what was bothering me. What I'm here to tell you is when we're doing these vectors and these triangles and stuff, first of all, the angle that we're 99% of the time interested in is the angle between the tails of the vectors. If you're careful about where you're putting your tips and tails, it helps a lot. The angle we want is the one between the tails. And second of all, we always want the angle as measured from the horizontal, because we speak English and we say, or whatever language we speak, in that language, we say things like southwest or northeast. And what we mean by southwest is how far south of west are we? We don't mean how far west of south are we? Okay, I'm getting far, but so what I'm saying is, if you want it to all work out and not all of a sudden fall apart at the end of the problem for lack of practice, what you do always, what I do always is when I'm resolving vectors, I always draw the horizontal first, and then from the tip of the horizontal, I draw the tail of the vertical. In other words, I go like this. And that is not obvious. That's something you figure out the hard way from practicing a lot. So here's what I'm saying. This is this triangle. This is E1X. This is E1Y. This is my angle theta 1 right there. Okay. Again, I mean, I'm not going to do this all again for the second one, but I'm really honestly telling you, all joking aside, I'm saying that triangle I just drew, it's one of those triangles where if I just draw it and you just write it down, it seems like, well, duh, and then I drew the triangle. It just seems like the obvious triangle to draw, but you don't find out until you practice this on your own, or until you're in the middle of some exam or something, that there's a million different options for what I just did. That's the right option. And I'm trying to save you a heartache from it. There's other ways it could have been done, and they get you into trouble, get me into trouble. So, okay, that's my zoom in on E1. Now, what's the point? The point is that therefore, if I've drawn it correctly, E1x is equal to E1 cosine of theta 1 because of SOHCAHTOA, because cosine of theta is adjacent over hypotenuse, therefore adjacent is cosine times hypotenuse. And similarly, I didn't give myself much room, but similarly, E1y is E1 times sine of theta 1. Okay, so now I'm going to calculate Now I'm going to calculate these components or compute these components with the numbers that the problem had given. E1x equals E1 cos theta 1. Okay, so what do I mean by E1? E1, the field, this is all comes from Coulomb's law. Again, we'll write it up here. Okay. So E1 is that number K times the charge Q1 over R squared times the cosine of theta 1. Okay, that number K. Now, that number K, you're not supposed to memorize it. You're always giving it, but you are supposed to have some perspective or some comfort with it. That number K is the electrostatic constant, the universal Coulomb constant. It's approximately 8.99 times 10 to the 9th newtons meter per Coulomb squared. Again, you're not supposed to memorize it, but you're supposed to know that it's huge. You're supposed to understand it's a huge number. It has a positive exponent in the scientific notation, unlike gravity, which is tiny and has a negative one. You also, if I don't generally do this, but say I just like literally asked you on a exam or something like, what are the units of this number? You should know the units. As obscure as they look, you should understand that they are newtons times meters squared divided by Coulomb squared. That looks really obscure, but you'll know you understand things if you understand that the units have to be that way because they're meant to cancel out the meters squared in the denominator of the field, and they're meant to cancel out the Coulomb squared in the numerator of the field expression. So that's what KE is. But again, now, because that is a crazy number and we're just trying to get a feel for what's going on, and this is a theoretical problem, we round. We say, and we did this last time in class, we're going to round that to 1 times 10 to the 10th newtons meters, because I'm spending all day as it is anyway, so we don't want to spend all day on that. So that's what I mean by KE. I'm going to flip the page. You can tell me to flip back if you want. Q1 is that charge that was given plus, 5 coulombs. Now, I should also quickly note, what I'm doing now is I am computing the magnitude of the horizontal component of the first field contribution. Like I'm computing the magnitude of E1x. I'm computing the magnitude of it. So, and how do I know about direction or whatever? I look at my tips and tails of my arrows. So I'm just computing the length of the arrow right now. Why am I screaming about that? Because I'm a screamer, but also because I'm not putting in pluses or minuses inside the charge number. Like the charge, as far as I'm concerned, is 5. Even if it were -5, I'm saying it's 5. I don't care whether it's plus or minus, is what I'm trying to say. Okay, and then R squared. I'm sorry, I mean R squared. Really, R1 squared. Every time I'm writing R here, I mean R1, because I mean the distance from point charge 1 to the, anyway, I mean the first R. So what is R? Well, Pythagorean theorem, right? Like that, I have a triangle there. R1 squared is 5 squared plus 4 squared, right? And please stop me if that's not clear. I'm looking in the chat. Okay. Like that's Pythagorean theorem. That's from the triangle. That's the distance there is, is 41. That's R1 squared. Finally, what's cosine theta 1? Well, that's a good question. You might say, I might say, when I first looked at this problem, or a problem like it years ago, I figured, well, in order to get cosine theta 1, I better get theta. And I guess I could get it from SOHCAHTOA or something. And then I better work. And then after getting theta, I better take the cosine of it. That would work. You can do that. But if you're going to do SOHCAHTOA anyway, you might as well skip steps. You might as well sit, and since this is going to happen every time in the problem, you might as well save some hassle and realize cosine of the angle in that triangle equals adjacent over hypotenuse, right? I mean, cosine always does. So the cosine equals 5 over the hypotenuse. And what's the hypotenuse? The square root of 5 squared plus 4 squared, right? So I hope that, right, like, and notice I have the square root here in this term. I didn't put the square root above because above is just r, above asks for r squared. The hypotenuse itself is just r. So at the end of the day, what I'm saying is this. Once. Second, I'm still here. I'm just. Okay. Huh. Okay. I'm just trying to get rid of that noise, but that's weird. Well, anyway, okay. And please stop me if you, well, just stop me if you're not following any of this. Yeah, okay. So this, what we have so far. What we have so far is not the answer, for good or for bad. It's not the answer of the whole problem. It's not. It is how hard in the horizontal direction Q1 is pushing on the origin, right? That's what it is. It's at the origin. It's that Q1 is pushing on the origin that hard to the west. I know the west because my whole arrow is going southwest, right? That's how it's pushing to the west. That means, just to be physical, if there was one positive Coulomb of charge at the origin, let me back up. Right now, there's nothing at the origin. The origin is just a point in space. There's nothing that is sitting there. We're saying just because there are objects sitting elsewhere in space, therefore there is a field sitting at the origin. There's arrow sitting at the origin, which is a force waiting to happen. We're building that arrow basically from four pieces, from two horizontal pieces and two vertical pieces. This is the first of the two horizontal pieces. This says that just due to Q1, if a one Coulomb charge found itself at the origin, it would be shoved to the west this hard. And shoved to the west. I don't mean it's going to move to the west that fast. I don't mean it's going to go that far to the west. This is the units of this, which I should have stopped and asked you, but I didn't. The units of this are newtons per Coulomb. Every one Coulomb that would ever find itself at the origin would be pushed to the west with this many newtons, right, to the west. And if it was an electron, or if it was one negative Coulomb sitting at the origin, it would be pushed to the east. Like, that's what we're saying so far. So this is one component that we've gotten so far. I actually am going to be thank God. Thank Quark. Someone in the direct chat is asking, okay, yes, absolutely I can. And perfect timing on your part, direct chat person. There's one person in the direct chat, so you know who I'm talking to. You know who you are. You asked at a perfect time because I was about to turn this work to you guys, so thank you. Okay, what someone's asking in the direct chat is, can I explain the third step of the math? How did I get 41 to the 3/2 power? Very fair question. So fair that I'm changing my voice as a result. Welcome to my bar mitzvah. Yes, I'm not making fun of you. I'm making fun of myself. Yes, the third step of my math. Oh yeah, because so I have 41 in the denominator. Well, here, okay. Yes, good question. Hold on. What I'm doing is this. I'm saying, well, I mean, the short answer is I have in the denominator, I have 41 times the square root of 41. So really what that is 41 to the first power times 41 to the 1/2 power. Right? I mean, this is like a math trick. I mean, I almost didn't, to be honest, I almost didn't even need to do that step, but it makes it easier for me to type this into my calculator. Like 41 to the first power times 41 to the 1/2 power, which is what square root means, 1/2 power. 41 to the first power times 41 to the 1/2 power is the same thing as 41 to the 1.5 powers. And this is a good question. And when I'm done in a second, you should tell me whether I'm being clear or not, whether you get it or not. Like if you go to the extremes, so you go to easier numbers, if you had 41 cubed times 41 squared, what we would say is that's the same thing as 41 to the 5th. Because exponents, when you're multiplying numbers with exponents, you add the exponents together. So this is 41 to the 3/2 power. Wait, first of all, does that, okay. First of all, maybe, okay, cool. No, thank you. I'm glad and I'm really glad the person asked. First of all, as you could tell, I'm just glad when anybody asks anything because come on. And please do submit for points, private chat person. But also, I'm glad they asked because it means they noticed, like, this is a pattern. I wrote down the 3/2 power really for two reasons. Like, one, like I just said, it's kind of now easier because frankly, what I do in my calculator, because this starts getting messy, right? Like there's scientific notation, there's order of operations. It's actually, to be really blunt, it's easy to follow it's not easy. It's possible to follow all this physics and then totally beef the numbers in a calculator. It's very possible to do that. One thing that physics is trying to teach us in the background is to have enough of the reason when I'm talking about all this stuff, I'm sure you've noticed, I'm very slow. I use a lot of words to say very little in a way, because like at every line of these computations, I'm trying to remind us of what the physical picture is at every step of the computations. That is a physics thing to do, as annoying as it might be, because what we're trying to do as physicists is we really are trying to physically picture the world. The computations are like, they're the grind, but we're supposed to be getting to the state where at the end of the day, when we get an answer from these computations, we should be able to look at it and go like, I think I made a calculator error. Like we're supposed to have a sense of what we're looking for way before we get there if we're doing physics, not raw math. And that's why we draw all these diagrams and yada, yada, yada. So first of all, I'm very glad the person asked. But second of all, the reason I then change it to 41 to the 3/2 power is, okay, number one, on my calculator, to be honest, what I really do then is I type the top number in scientific notation. Like I type like 2.5 EE11, if you know what I mean. Okay, actually, to be really honest, because I have a cheap calculator, I do parentheses. I do open parentheses, 2.5 EE11, end parentheses, right? And then I hit divide. And then what I do on my calculator is I type 41 caret, that caret thing, that upward, that caret thing. I hit 41 caret 1.5 because 1.5 is the same thing as 3/2, right? And I don't have to write like 3 divided by 2 or something, which is yet another operation in the calculator. So I write 41 caret 1.5. I write the top thing with parentheses divided by 41 caret 1.5 and hit equals. And then I can trust that the answer I got is actually what I'm looking for. Like it reduces a lot of order of operations shenanigans and stuff like that. So anyway, I don't know if that helps anybody, but the calculator shenanigans are hard with these kind of problems. So number one, that's why I do that. But number two, I'm also glad the person asked because this is a pattern. I'm about actually, as you might have noticed, and you should still ask more questions if it's not clear. I'm about to turn the rest. There's 3 more components that have to get done. Okay. I'm going to turn that to you guys now. I'm not even going to worry about breakout rooms. It's not going to take that long, but it'll take you faster to do 3 components than it will be for me to talk about one of them. So you'll see this pattern that we just did. It's going to happen every single time. You're going to have the same number in the denominator twice. Only one of times it's going to be to the 1/2 power, and one of the times it won't. Hopefully you'll know you're doing it right if that keeps happening, because every single time we're doing r squared in the denominator times either a cosine or a sine. In other words, times a hypotenuse, which is r. So I'm partly trying to emphasize what the pattern of the computation is. Wait, okay. So presumably that person I think that person said that he or she understood. So I'm going to say now to all of you, I'm not doing breakout rooms. I'm not leaving. I would like you to follow the pattern I just did and just get the other 3 components, which means E1y, E2x, E2y, do the exact same thing I just did. For the other vector, you'll have to zoom in on and make a little picture. Maybe I'll do that. I'll do the picture while you're doing, but you should get 3 more numbers. I'm going to warn you right now, or I'm going to suggest don't worry about positive or negative signs. Our pictures will take care of that. Just get 3 more numbers. They will all be to 10 to the 8th. I'm 99.9% sure. You'll get a total of 4 numbers, all of which are to the 8th order of magnitude. So if they're not, you've done something wrong. Also, if you were paying attention to the beginning part of this conversation, you'll be correct to expect that your numbers for E2x and E2y should probably be smaller than your numbers for E1x and E1y, because of the thing that many direct chat people already explained. So I'm going to say to you guys, please now get the numbers, the next 3 numbers. As you you can do one at a time. As you get each one, you could put in the direct chat and let me know, or you could put questions in the direct chat or whatever. If you're really, really stuck, it would be really helpful if you even put in the direct chat, I know what you're asking, but I don't know what to do, or something. Just show you're alive. Okay. I'm going to shut up. But what I will do is while you're doing that, I have the numbers too. Yeah, no, I'm going to turn off my screen and I'm going to do it out so that when we reunite, there'll be a little time saved. I'll just have it there for you. But okay, or just raise your hand if you know what I'm asking you to do now. Well, raise your electronic hand if you know what I'm asking you to do. Okay, thank you. Awesome. Okay, awesome. Thank you. All right, for your physical hand. Okay, great. Thank you. All right, I'm going to shut up. I'm going to turn off my screen. And obviously, if you guys have a Discord or whatever, of course you could communicate with each other. That would always be awesome. Or if you're sitting next to each other somewhere, feel free. But my 9-year-old so badly wants me to put him on Discord. I so don't. Okay. Okay. Oh, he's in the chat, sorry. So busy. Oh. Oh. Thank you. I thought, okay, yes, I am sharing my screen, but I thought, okay, thank you. I, okay, I was meaning to, okay, thank you. Wait a minute. 1 second. Okay, so, and again, so you guys are doing this, I would, well, yeah, I do think this is a long calculation, but it would help if, a couple of, well, we're gonna wrap in a couple of minutes, but if anybody's gotten even one answer, I'd love to see it in the chat, or one question or whatever. Well, anyway, we are gonna reunite in a couple of minutes. Oh, and I will even say this, I'm going to interrupt this broadcast, this program with the broadcast. I'm not seeing a, what is going on? For what it's worth, I think the fourth component actually is order of magnitude 7. I don't know if you're up to it or not. When you get to the very last one, you'll get something to the 10 to the 7th, and that's not a problem. I mean, it's not what I predicted, but it is true. And anyway, so I'm actually thinking that most of you are more efficient than I am. So I'm thinking that if I did all the 4 components, it would be nice to start seeing from some of you some feedback, even just on the first component would be nice. Either in the direct chat, give me an answer to the first component, or give me a place where you're stuck, or give me a surrender. Again, we're not going to be doing this all double period. Like when we wrap up this problem, I mean, for good or for bad, this is the end of this homework sheet. When we wrap up this problem, then I want to shift gears entirely and talk about the lab with you, or the labs with you. So whether that's an incentive or disincentive, I would like to soon start hearing from you in the chat about these components. Okay, I'm gonna say. I don't know what this all is. I know some people ask me if they could step out. This is, all right, well, can I send a broadcast? I'm gonna say in like at 4:45, I'm gonna start going over this, but I really would like some feedback before I do. I don't want to just talk into a black hole. And I'll honestly say again, this is one of those computations that is it once you do it on your own, if you follow my model and you do the other three components, then you'll reduce it to what some of you have appropriately called it. If you get the other three components on your own, then you will view this all as sort of repetitious and not hard and straightforward. But if you don't practice the other three components based on what I just did on the first, then this is a very overwhelming computation. I mean, it is an overwhelming computation, I think. If it's broken down into steps, it's not, but it is if it isn't. So what I'm strongly urging, what I'm asserting is that I'm not going to actually start talking about it until I get some feedback in the private or public chat. I would like to see some answers or specific questions of where you're not getting answers or something. And if honest, and yeah, so I'm ready to go, or I could be ready to go when you guys are, but I'm going to wait until something is happening in the chat. Do I sound like I don't know what I sound like. A man in search of a real, of something, but okay. So, okay, I'm going to put that in the chat though. Okay, I see something. Oh, could I show? Oh, do you not have the PD? Okay, wait, sorry, I didn't see this in the chat. Can I show you the model one more time? I mean, the answer is yes. Oh, because you don't have the PDF, because it's not on the screen. Yes, I can. Hold on a second. I'm not gonna, I mean, I can display it on the screen, but I can also say that that's what we were supposed to be doing in class before. Hold on. Well, here, let me share the. And I know there's something else in the chat. I'll look at that in a second. Let me just put this up on the screen. You do this. Okay. So, in fact, okay, well, no, I won't do. Okay, so this is what I'm talking about. What we just did, and presumably you were taking notes when we did it. Just say, oh, wait. There's a very good question in direct chat. Also, I'll answer that in 1 second. But this is the model I'm talking about. But you might want to screenshot that, I guess, because it's a couple of pages. Excuse me. In fact, the key to it is right here. This is really what I'm talking about right here. That's what you're doing for each of the. But guys, also, I mean, I'm trying to be sort of silly and sort of nice, but really, like, this is class. You know what I'm saying? Like, I think maybe we're spending a disproportionate amount of time allowing you to get. I mean, I think let's just do this. You know what I'm saying? Could I say this more firmly? But okay, wait. Wait, and this. Oh yeah, we should wrap this. Okay. It's now actually is getting late. This ends at 5. It is getting late. Okay. Okay. Okay, I'm gonna start. Okay, folks. It is 5. It's not the thing I wanted to do all period. Well, I have heard from one person in the chat about something substantive, but it's one person. So I'm going to assume, well, I don't want to assume the worst. If someone could put one component in the chat, not the person that I have been hearing some like there's one person that is asking me questions, that's fine. But other than that person, if somebody could put one component in the chat, I will feel a lot more comfortable going over this. If I can't get anything in the chat, that's a little awkward. And I don't care if what's in the chat is wrong, but I would like to think that what everybody just spent the 40 minutes on was doing something. Thank you. That's helpful. All right. I mean, I appreciate the 2 videos. I mean, God, and I'm okay. The awkwardness is about, I realize we're about to be interrupted. So that may save us from some kind of unanticipated ugliness. I'm ready to go over this, obviously, but I feel like it's very silly for me to go over this if I'm really just talking to myself. I know thank you. I see something in the chat. Okay, that's helpful. Thank you. We are about to be interrupted by my erstwhile son. That may save us. I do see an answer in the chat. That is good. Thank you. That may help us too. All right, I may go with that as the one and only. I mean, now I'm stalling because I know we're about to be interrupted by someone about to be walking in. But I will say this is not like, I know it's a long period and it's on Zoom. I know it's torturous, and it's torturous no matter how we do it, but it's like, it is a waste of everybody's time if we're not using it. And well, okay, is that another? That's not another. So it's a little bit disturbing if I'm only seeing one thing in the chat. But okay, no, but I asked for, I see 2 things in the chat. So, all right, I am gonna start there. But I'm not, but you know what, all right, but I'm just gonna say the answers because it is, well, here comes the interruption. Okay,
Yo, Dad.
Yo.
I won the raffle.
You did? Awesome.
Yeah.
What? Oh, that's awesome. What?
This is what I got.
Oh, that's awesome. Okay,
Everybody, I won the raffle.
Okay, that's Okay.
This is what I
Oh,
got.
that's awesome, actually. That's great. Okay. Okay. That is, congratulations. Is that because you bought 400 raffle tickets? Okay. Well,
5.
100. Okay.
And
Well,
Joe's bought 20.
Well,
Joe's
that-
bought 20. I got 5, and I still won.
That just shows you.
Sorry, Jonas.
All right. I think Jonas is in a different place. But awesome. All right. I'll come up soon. and we'll-
Jonas is not here.
Okay.
Jonas.
Okay.
is dead.
Okay. Okay. But awesome. Mazel tov.
Ow.
Okay. Okay. I'm psyched. Our money went to a good cause. Okay. All right. So I'm going to say these components now. You definitely can stop me if you have specific questions. Oh, thank you. Oh, so now they're okay.
For the last time.
Okay. Don't
He
not this
does
class.
not give you homework.
Right. This class does not need to hear that.
Got
Okay.
it.
Okay. Got it. Okay.
If
okay.
he does,
Okay.
contact and
Right.
no spelling test.
They won't have
If
a
you test or anything, tell me. If he gives you a test or homework, tell me.
all right.
I will tell your boss again.
Don't worry, they won't do it anyway. I mean, what? Okay.
Oh,
All right,
good.
so that, go. Okay. All right. Well, that's why I have no authority over either province of my life. That's for sure. Okay. So now you congratulate Murray. I don't know whether to be touched that you heard all that and you congratulate him. Okay. Well, I appreciate your congratulations. All right. Look, so this was the first component. This is the second component. Okay, I'm not trying to be rude, but I mean, here is the second component. I did the exact same thing as the first component. The only difference is it's now the y component. So it's times sine of theta rather than cosine of theta. Sine is opposite over hypotenuse rather than adjacent over hypotenuse. So there's a 4 in the numerator up there above the square root of 41 instead of a 5. Like that's literally the only difference. So we get this for the y component of the first contribution. Then we go to the other contribution. That's my little zoom in triangle of it. It's not to scale, but notice it is much longer in the horizontal than it is in the vertical. So I do the exact same calculation on the second one. I do the x component first. It's the same computation as before, only it's cosine of this angle, and it uses these coordinates. So the coordinates are 10 and 3. So the hypotenuse r squared is 10 squared plus 3 squared rather than 5 and 4 squared. And the charge is different. The charge is 2 rather than 5. So I'm just plugging into the same thing as before. Cosine of this angle rather than that angle, adjacent over hypotenuse, the adjacent is 10. So this is that component. This is the third of 4 components. And of course, I'm going to upload this PDF when we're done. So hopefully that's, and then this is the last component, which is a little bit smaller than all the rest, the y component of the second field contribution. So now what do we do? And there was one person in the chat that I'm very impressed and pleased and gratified. One person in the chat did recognize what to do next. I'm not going to single out that. I mean, I'm almost tempted to have that person explain. And if that person wants to, if they want to put in the direct chat that they want to like explain this or present it, that would be lovely. But I'm certainly not going to force that. So I'm just going to go unless I see something in the direct chat. If the person wants to present, that would be lovely. But I'm watching the chat. But oh, okay, fair enough. Fair enough. That's I know the feel. Okay, but I'm going to keep going then. Okay, so what do I do now with these 4 components? But I do recognize that somebody in the room knows. What I do is the whole idea is a 2-dimensional problem is really 2 one-dimensional problems occurring simultaneously yet independently. So I divide the world into an X world and a Y world. I add up all the components that we just got, but I add them individually along axes. So the first So these are the four components that we're going to add up. But now I have to take my triangles seriously. Now, there is a reason that I cared about those tips and tails. For example, in the first vector, the contribution from the first point source, the whole vector was pointing southwest. It was pointing south and west. So it was pointing west and it was pointing south. Each of those components gets a negative sign. In other words, positives and negatives apply independently to each axis. And the other vector, E2, was pointing north and east. So both of those vectors, components, don't get negative signs. They get positive signs. So now we add up. We're literally adding tip to tail, the total effect of the field on that point. So we get and then as one person in the, so what is this? This is us almost being done with this problem. What is this? This means in the end of the day, the final vector that we're solving for pushed things to the west with approximately 7.7 times 10 to the 8th. Oh, sorry, I shouldn't. That's correct, but I shouldn't draw it there. Hold on a second. The final vector, this is another example of what I was saying before. We draw horizontally and then vertically. So the final vector pushed all the way to the west, 7.7, 10 to the times 10 to the 8th, and it pushed south almost as much, but not quite. So this is a little bit not to scale. It pushed to the south at 7.09 times 10 to the 8th. So the final answer that we're looking for, the final precise version of that blue vector that we predicted from the start, this should be and the final angle, as someone in the direct chat pointed out, the final direction should be the arctan of those final two components. The final answer of all of this monstrosity, the final answer is that the field, and actually the people that did put anything in the chat, if they want to confirm or deny whether they got this final answer or especially if they just think I'm wrong, I would love to hear it. But I think the final field strength is approximately 1 times 10 to the ninth newtons per coulomb. And the final direction of the field is 42.3 degrees approximately to the southwest, as we predicted, to the southwest. And what this means at the end of the day, is that if a 1 coulomb positive charge, I just thought of a problem that I should ask you, but if we put a 1 coulomb of positive charge at the origin, it would be instantaneously pushed with this many newtons, 1.05 times 10 to the 9 newtons, in that direction, 42.3 degrees southwest. Like, that's what all of this means. This is the force that's waiting to happen and waiting to be exerted on a positive 1 coulomb of charge that might arrive there. If a 2 coulomb of positive charge arrived there, it would get pushed with twice as much force. If a negative charge ended up there, it would be pushed the opposite way to the northeast with this strength. If 1 proton ended up there, then we'd have to multiply this field strength by the charge of a proton, which is 1.60 times 10 to the negative 19th coulombs. That's what this means. And I'll say one last final thing, and then we're just going to move on and hopefully shake things up a little bit because we still do have a little time. This is the final field vector that exists at the origin due to those 2 point sources. If this were real life, or if this were an exam or anything, we could ask the exact same question. We could ask for the same computation for any point in the whole Cartesian plane. Like, the point is, there's now vectors everywhere in the Cartesian plane, everywhere in space. At every point in space, there's a different vector sitting there that is the result of the vectors being combined from those 2 original point sources. This long computation, of course, I made a lot longer by talking about it and by being awkward and everything, and we made longer by like having time to sit and think about it. But what I want to say is, it's not a short computation under any circumstances. Like, it's a lot of work to do, even if you do it perfectly efficiently. It's a bunch of work to do just to get the field resulting from 2 dots. I do want you to appreciate that that's what we're saying here, that you have 2 dots in the lab, like just literally 2 proton, or a proton and electron. Like, what we have here in effect is one hydrogen atom. And in order to compute the effect of 1 hydrogen atom at 1 point in space, a few centimeters away, we had to do all of this work. That's a lot, considering it's just 2 dots. You can imagine that in order to get the fields due to more realistic situations, like lots and lots and lots of dots sitting in a wire, sitting in a circuit in a lab, there's either we do a lot of work to figure out what the field effect is of a long line of charge, or we must have other techniques and other models and other ways of extrapolating from this picture to the more complex pictures. And of course we do. But this is to appreciate what's going on the micro level of field creation. So now I'm going to shift gears now for good or for bad. I want to shift gears now. Okay, I want to shift gears now. We have 28 minutes or so. I was hoping to spend a little bit more time than that, but with the 20 minutes we have left, I want to shift gears. I hope you're there. I want to hear from you in an informal way. I want to hear from you what has been going on. I mean, I of course I know from my perspective, but I want to hear from you what's been going on in lab this week. Yes, what went on in lab this week? Particularly, specifically, what I'd like to know is what was the takeaway? What was the proposition that you affirmed or denied? What was the conclusion that you took away from lab this week? And I'm actually going to start by saying, could you raise your electronic hand if you're in the room, like hearing me right now? That's good. Okay, that's encouraging. That's a good. Okay, thank you. I didn't even need Felix for that. Okay, great. That is helpful. Thank you. I can live again. So does anybody in any way informally, you could like unmute, you can use your voice, you could go in the chat. I just informally just tell me anything. And it's not a quiz, but I would like to start helping you with lab, but it's better for I can only help when I know what I need to help with. So could someone give me a summary or just any, or if you want to go directly to something you're confused about, a question in lab, but let's talk about, and if you still have your hands up from before, you could put them down, but if you, okay, well, that's honest. I see something in the chat. All right, I appreciate your honesty in the chat. That's something. Okay, and it's one person right now, so the person who just said about being sick, I appreciate that. But can anybody else tell me anything about lab, either a takeaway, something you got out of it, or a question you have about it? Oh, okay, that's good. I see something in the, okay, that's helpful. I see. Oh, and if you're raising your hand to say something, go right ahead and say it. If you're raising your hand from before, you could put it down. But if you're raising your hand because you have a question or a statement, please just go ahead and say it. But I do see one thing. I'm going to wait for one other thing in the. I see one. Okay, cool. I see two. Okay. Oh, cool. Okay, that's good. That's helpful. Okay. All right. So I see two things in the chat. Oh, that's another. Oh, thank you. You okay? Sorry, this is helpful. I mean, I'm beginning to lose my. Oh, a lot actually in the chat. Okay. So, oh, very specific. Okay. Okay. Now it's getting very specific in the chat. Okay, that's good. Thank you all. I mean, and there's more. Okay, that's funny. Okay, big voltage, big light track. Yes. Okay, fair enough. All right. I actually did just get a lot of reassurance and a lot of specificity in the chat. And I appreciate it. I am gathering that you've, number one, been doing circuits in the lab. That's good. That was my impression as well. It's good to have that confirmed. Number two, I'm seeing in the chat that in your investigation of circuits, there seem to be two kind of basic takeaways here, which is great. One basic takeaway seems to be, in fact, let's start writing them down. Here are the two takeaways as I understand it. One thing is you're telling me that electrical current is directly proportional to what we're calling voltage or electric potential difference, right? And remember that symbol means directly proportional, right? So, okay. And I agree, by the way, I totally agree. In fact, I'll even cut to the chase and say that the exact equation, which I'm not sure, tell me if this is familiar or not. To my mind, the exact equation, which you may or may not have seen, is that current is equal to electric potential difference, i.e. voltage, divided by resistance. I don't know. In fact, could someone just tell me in the chat, just on a factual level, have you seen that? Has resistance been mentioned explicitly? I'll pause on that question for a second. Well, could someone just confirm or deny whether this equation that I just wrote is or is not familiar yet? You could say no. Hello, we're losing again. Houston. Okay, good. Oh, you did. Okay, great. Not, but wait, we did. Wait, not gone into detail is fair, not familiar. But wait, but then one person is saying that you did. Interesting. Okay, slightly inconsistent responses here, but okay. All right, but I'll table that for the moment. What we're definitely saying is, we believe, is that current is directly proportional to oh, that is the one. Okay, so that. Oh, it does make sense. Okay, I'm seeing the director, and thank you all for participating so much in the chat now. Now we're really rolling in the last two. So yeah, so one of the motions really was about resistance, but it sounds like maybe that didn't land with the whole class yet. And that's fine. Okay, so this is helpful to me. So now I see where you are. At least we're all agreeing, even we put aside the question of resistance, we're all agreeing that current and voltage are directly proportional. And then are we also all agreeing? It sounds like the other big takeaway that you're telling me, and this is pretty important, you're also telling me that you investigated the difference between series and parallel circuits, well, you actually, I don't know if you use those words. Hold on a second. Did you? Yeah, you did. Okay. Okay. It seems like those are the two big things you're investigating: the relationship between current and voltage, and the relationship between series and parallel. I am going to, because I think I'm being very dry and overly mathematical for much of this period, I'm going to go over these in. Wait, hold on one second. Hold on. Okay. I'm going to go out of order here. Okay. Okay, I'm going to go out of order here. I'm going to deal with the series versus parallel thing first, and then back up to the current voltage thing. Wait. Okay. First thing I want to say about series versus parallel, since it sounds like that is what you were investigating. I want to try to clarify exactly what we mean by series versus parallel, because they sound like series versus parallel sound like shapes. I mean, it sounds like parallel sounds like a geometry thing. Like if two things are in parallel, it sounds like they would be arranged in two parallel lines. And that does not necessarily have to be the case at all. It doesn't have to refer to the way they look. But also series versus parallel sound like two different ways to describe a circuit. You'll hear in life a lot of times like, oh, this is a series circuit or this is a parallel circuit. And that's a misconception. That confuses the issue. A circuit does not have to be identified as one type or the other. A circuit could involve lots of series configurations and lots of parallel configurations. What series versus parallel are two different configurations, the two possible ways to configure a pair, any pair of devices. Okay, so two resistors or two light bulbs or two doorbells can either be arranged in series or they can be arranged in parallel. When they're arranged in series, what that specifically means is no choice. That specifically means all the current which exits the first device must enter the second device. That's what series means. Literally, it means literally no choice. Every bit of charge that exits one device must enter the other. Like that simple. That's what series means. And again, it refers to two particular devices. You can say that two light bulbs are in series with each other, or you could say that two resistors are in series with each other. What that has to do with anything else in the circuit could be then those two things could be in parallel with other stuff or whatever. But a pair of devices could be in series, or they could be in parallel. If they're in parallel, okay. Parallel means exclusive choice, exclusive choice. Every bit of current, every charge must either flow through one device or flow through the other. No charge can flow through neither nor both. I'm being like overly explicit, but we have to be. It's a literal exclusive choice. If you say that two light bulbs are in parallel, that means, and I should say, and sorry, then all charges reunite. So a parallel configuration, if we say that two bulbs are in parallel, we mean there's a fork in the road. We mean that all the current is coming toward, flowing in a wire, and then reaches a junction, reaches a choice where some of the current will go one way and the remaining current will go the other way. And every bit of current has to be accounted for, right? This is what parallel literally means, that every bit of charge that you consider is either going to go one way or it's going to go the other way. But no bit of charge is going to go both ways. No bit of charge is going to go neither way. And then at the end, after they each fork in the road, somewhere in the circuit, maybe not right away, but somewhere they all reunite. So that's what parallel means. It doesn't matter how it's geometrically arranged on the table. And I'm watching the clock. Wait, okay. And there's conclusions that we come to about series and parallel configurations. What we find is well, I'll just read this out loud. If two devices are in series, if two light bulbs are in series, then if you measure current through one of the light bulbs and you measure current through the other light bulb, the answer you get for current has to be the same for both the light bulbs if they're truly in series. Because what current is flow. Do I want to say, hold on. Because what current is flow. What current is in English, in intuitive terms, current is, well, okay, I'll write this. Wait, what I'm saying right now is the definition of current, the definition of average current is amount of charge that passes by a given location per a given amount of time. If you stood in the wire and counted the number of coulombs of charge that flow past you per second, you'd be counting current. That's what an ammeter is doing. 1 unit of current equals 1 coulomb of charge per 1 second of time. So current is how much charge is passing by a given point in space per a given time. It's flow. Well, yeah, it's flow. So if that's the definition of current, it stands to reason that when two devices are in series, the currents through each one of them must be the same because every bit of charge is accounted for on the way out of one. It goes on the way into the other. So there's no reason that the charge count should change. On the other hand, and this is where we're going to end. I know we have 9 minutes. If two devices are in parallel, the currents through two devices in parallel do not need to be the same, and they generally aren't unless the devices have the same resistance. Like if there's a fork in the road, some current can go one way, the rest of the current can go the other way, and there's no reason to assume it's the same amount of currents going each way. However, the voltage across each device will be the same. I'm saying current through devices in series is always the same. Voltage across devices in parallel is always the same. Well, why would that be? That must be because of what the definition of voltage is. Okay, and I know we have 5 minutes. Current is flow. Current is a rate. Current is how much charge passes by a given point in space throughout a given interval of time. That's what current is. Voltage is the nickname for electric potential difference. Electric potential difference, hold on, please. Okay, electric potential difference. And I know we have 4 minutes. Electric potential difference is a bit more abstract. If current is charge per time, electric potential difference is really field times space. And that's really what it is. The electric potential difference is the voltage, is not something that's measured at a point. Electric potential difference is really a comparison between 2 points. It's something that's measured over an interval, a region, a space between 2 points. To measure electric potential difference, what you're really measuring is how much more unstable is one location compared to the other. Why would one location be more unstable than the other? One location would be closer to positive charges than the other. One location would be more stable than the unstable than the other because it's harder to get a positive coulomb of test charge to that location. The amount of work that we would have to do to bring a positive charge across a field to one location relative to another is the voltage that that one location has relative to the other. What bottom line, 1 volt of electric potential difference is really 1 joule of electric potential energy per 1 coulomb of charge. So with 2 minutes left, current is flow of charge per time. Current is something that's measured at a point in a line. Voltage is something that's measured between 2 points. It's how much energy a charge would gain falling from one point to the other, or how much energy would be required to bring one charge up from one location to the other. So, and this is the last thing I'm going to say, for a circuit to work, energy must be conserved. The whole premise on which circuitry rests is the conservation of energy. Energy is conserved. If a charge gains 9 volts coming out of one terminal of a battery, it's going to lose those 9 volts no matter what route it takes to get back to the other terminal of the battery. So no matter what choice it takes, whether it goes through this light bulb or that light bulb, every single charge in a circuit has to conserve energy and gain and lose a total amount of whatever energy the battery originally gave to it. So 2 devices in parallel are 2 devices in a choice. Whichever choice you make, you've got to lose the same amount of energy in order for the whole circuit to work and all the charges to be reunited after the choice. Therefore, 2 devices in series always have the same current, because current means flow, and 2 devices in parallel always have the same voltage drop or the same potential difference across them, because voltage means energy change. Okay, that's all we've got for today, for good or for bad. I hope that clarified anything. There's no new homework due next week. We'll just leave it at that. So I'm here and I will continue to go through the tests. The tests are just coming back one by one in all the classes. I apologize, they're not coming back in a group. You'll get your exam when you get your exam, and it reflects where you are in the alphabet more than anything else. So I'll stay here if there's any questions, but other than that, have a great weekend and a great week.
Thank you, Professor.
Thank you. Thank you. Thank you. Have a good rest of the week. Yes, or weekend. Thank you.